So the last video, we ended here where we took a very simple example of a first-order linear homogeneous equation to just see that there's a connection between the solution of such an equation and the root of the characteristic equation. Now, first-order equations are not going to be our focus because these are very simple. We've already covered first-order equations and more complicated ones than this. This kind of first-order equation, which is a linear homogeneous equation, is actually a separable equation, and that's why the solution is very easy to find. We just illustrated that. We noticed that the exponential function we get as the solution, the number appearing in the exponent, minus 5, is actually the root of the characteristic equation. And we want to now illustrate that this is no accident, and this actually works for higher order equations. The problem that we're going to see is when you get to higher order equations, your characteristic equation could be a quadratic for second order equations or a cubic equation for third order equations and so on. So different possibilities are going to arise. For right now, what we're going to focus on is what happens when the characteristic equation actually factors into different roots and gives you distinct roots. So in this case, we talk about quadratics. We're going to talk about quadratic equations that have two distinct real roots. And we're going to see that those two real roots are going to tell us what the two pieces of our homogeneous solution are. So our homogeneous solution is that function y sub h, and we're going to make it a sum of two functions, some constant c1 times y1 plus some constant c2 times y2, where y1 and y2 are going to be of this exact form, of this exponential form, and the numbers appearing in the exponent are going to correspond to those roots of the characteristic equation. And this works for third, fourth, and higher orders. So let's look at this second order equation. Again, look, it's a second order linear equation by the form here, and it's homogeneous because the right-hand side is 0. The characteristic equation we obtain by just direct translation to this algebraic quadratic equation in the variable r. And in this case, this can be factored. And you can always use the quadratic formula to find the roots. But in this case, it's easy to factor as r plus 1 times r plus 2. Remember what that means is if you have a product of two expressions that equals 0, then it must be that either one or the other has to be 0. So there's two possibilities of making this equation true, either letting r be negative 1 or letting r equal 2. So what does this r plus 1 term tell us? Well, if we look at this linear equation on its own, it translates to be the characteristic equation of this first order equation, y prime plus y equals 0. And we know how to solve that from our observation. Since the root is negative 1, a solution would be e to the negative x. All right, e to the negative 1 times x. Now if we look at the other part, the r minus 2, that translates into a first order equation, y prime minus 2y equals 0. And again, in this case, the 2 becomes what we see in the exponent. So we want to identify now is understand that both of these solutions are not only solutions of these first order equations that we have here and here, but they both actually have to solve the second order equation that we have at the top. And the reason for this is this algebraic factoring of the characteristic equation actually translates into a decomposition of our linear operator defined by the left side of the equation, this L of y. We'll actually be able to write it as a composition of two linear operators, two first order linear operators defined by both of these expressions. So for this example, the general solution becomes just adding constants in to obtain the general form, and then if we had initial conditions, we could figure out what those constants are. So let's see why this works. So this is our linear differential operator. We've already identified that there are two roots to the characteristic equation, negative 1 and 2. Let's look at those two pieces separately and define linear differential operators. So the r plus 1 translated into this, what I'm calling L1 of y, which is a first order operator, and the r minus 2 equals 0 translates into this second first order operator and second first order equation, and I'm calling L2 of y to correspond to that term, or that factor of the quadratic characteristic equation. Now let's see how this product of these factors, r plus 1 and r minus 2, give us the characteristic equation. And let's see how that product translates into composition of these two operators, to see that it makes sense that both of the solutions to either of these simpler equations actually solve the overall equation involving our second order linear operator. So here's what my claim is that our L of y, which we have up top, can be written two ways. It can be thought of as a composition of L1 composed with L2, or L2 composed with L1. What that means is, let's think about this for a second. This being true, the function that satisfies L2 of y equals 0 makes what I've highlighted 0. And since L1 is a linear operator, and we saw before in earlier videos, L1 of 0 has to be 0. So the solution for L2 of y equals 0 will be a solution of L of y equals 0. Similarly, if L1 of y is 0, we find a solution to that, which we have found already, then L1 of y is 0, and then L2 of 0 is 0. So let's see how this works. In one direction, let's look at L1 of L2 of y. Well, what is L2 of y? Let's plug in what that means. It means y prime minus 2y. So this is the same as writing L1 of y prime minus 2y. Now what does L1 do? It takes whatever you have as your input, it takes the derivative of that, and then adds to it the function itself. So the derivative of this is y double prime minus 2y prime, and that function itself is y prime minus 2y. Now if we combine like terms here, what do we get? We get exactly what we get up here at top for L of y. So what we've just proven is that L1 of L2 of y is the same as L of y, which tells us that any solution of L2 of y equals 0 is also a solution of L of y equals 0. Now we do the same thing in the other direction, and we see that that works as well. Now we're taking L1 of y on the inside first. So L1 of y is y prime plus y. We're going to plug that in to L2. L2 says to take the derivative and then subtract twice the function. So we're going to take the derivative of this, which is y double prime plus y prime, and we're going to subtract 2 times that function, y prime plus y. Again, simplifying and by combining like terms here, we get exactly what we get for L of y. So again, we've confirmed these two equations that I've claimed here in the middle. And this confirmation is nothing you'll ever have to do again. You don't have to redo this. This is just an observation to understand that we reduce higher order equations to solving lower order equations, and then each lower order equation gives us one piece of our general solution.